Hi everyone, a very good day to you. Mr. Chu over here again, and I'd like to show you through this lesson over here, a very short lesson, how the Newton's second law can be applied to situations where the mass is not constant or the mass is changing. So let's consider this situation where you have a conveyor belt going at constant speed with sand continuously falling onto it. Now there is a dilemma which I will guide you to see. Take a look over here. Speed is constant over here, hence velocity of the belt is constant. So if you use F equals to ma, it should be 0, which means that no force should be acting on the belt. But we know that as the sand falls onto the belt, if we were to magnify, say using this circle as to represent the sand, there is a force by the belt on sand. And therefore, the sand will exert a force by sand on belt. So it will slow down by Newton's third law because there's a force acting over there. That the belt will slow down if there is no constant pulling force on the belt this way. So therefore, we got two different conclusions. That one, there is no force acting on the belt. Second, by Newton's third law and the analysis over here, there is a force that you need to exert on the belt towards the right, so that the speed is constant. So what on earth is happening? I think it is quite clear that intuitively you expect that there is a force that is required to pull the belt this way so that it maintains the speed even though the mass is, even though the speed is constant. So how do we reconcile that this expression is telling us that the force is 0, but common sense or using another route of reasoning, it tells us that force is necessary. So we have to go one up from F equals to ma, because the mass of the belt actually over here is changing, so we cannot just use ma. Now we've got to go back to the original definition of Newton's second law, that is the force applied, or the net force, important for you to use the correct language, net force is equals to the rate of change of momentum. So represented by this mathematical notation over here, dp dt, that is d by dt, rate of change of momentum, where momentum is equals to mv. Alright, so the way that we can handle this mathematically is that the d by dt, m times v, can be further broken down into mass dv dt plus v dm dt. So what on earth is happening here where we can have ma or v dm dt? Now it is interesting to note that in this case, the ma factor over here is 0. Why? Because the speed over here is constant. So therefore, you've got a situation where this is equals to 0. But if you take a look at this v dm dt, what you have over here is that the mass is constantly changing. So if I drop 5 kg of mass of sand every second over here, and this is moving at 10 meters per second. So if I use this part of the equation, I first of all know that the force is not 0 because the mass is changing and the speed is not 0. So I can actually calculate the force that's required to pull the belt at a constant speed. So I just need to take 5 times 10, I get 50 newtons. So that's why I mentioned earlier on in the earlier video that you need to be very careful that are you applying Newton's second law onto a case where the mass is constant, like the masses that we talk about, the man and live and man, the two boxes connected together, or a situation where the mass is changing. Another situation where you have to apply Newton's second law in this way is a situation where, say for example, you have helicopter. Pardon me for the bad drawing. Say this is the helicopter sweeping air and blowing it downwards at speed v. So imagine that the wing, the rotor sweeps an area of A and pushes the air downwards at v. So what is obviously the fact that the helicopter can stay afloat means that the force, the blades must be applying a force on the air downwards. By Newton's third law, the air exerts an upward force on the blades that is lifting the helicopter upwards. So the fact that the air is being pushed downwards means that there must be a change in momentum. There must be an F equals to dp dt over here. If there's no change in momentum of the air, there wouldn't be a change, there wouldn't be a force. I mean, if there is no force, there wouldn't be a change in momentum of the air. So let's take a look at how we can apply this law in this context. Assuming that the density of the air is rho, okay, density of the air is rho. Now, do you agree that it pushes a column of air of length L in time t downwards, then the speed that it gains, of course, is v, that's indicated over here. The mass of air that gains this speed in time t is equals to the length over here times the cross-sectional area, that's the volume, times the density, that gives you the mass, divided by t. This is your dm dt. The v times dm dt. Remember we talked about that? So what you have over here is that L divided by t, the length of air column pushed down in time t is also v. So you got a rho v squared. Now this is the expression that can be used in situations where you have air being pushed, you can have jet of water being pushed out, you can have jet of exhaust gas being pushed out of a rocket, you can have jet of hot air being pushed out by a jet plane, from the engines of a jet plane. So this equation applies in all situations where you have continuous mass, stream of mass of substance that gains momentum. But more importantly, I wanted you to realize how the Newton's second law is being applied differently for constant mass and for continuous mass. It is a very useful equation that you can remember, but it's good if you know how to derive the expression over there. Alright, I hope this is useful for you. Now that you have covered Newton's second law for fixed mass and for constant mass, we'll move on in the next video on conservation of momentum, where it's also an application of Newton's second law and third law, and which results in the conservation, which can derive the conservation of momentum. And I'm going to show you how we can handle different situations effectively and efficiently in the next video. Thank you.